Thank you for stopping by our poster at ORS2023. My name is Soroush Irandoust, and I am a postdoc at University of Wisconsin-Madison. I am excited to run through the poster in this video. Condylar stress fracture of the fetlock is a common fatal injury in thoroughbred racehorses. The distal end of the cannon bone experiences large cyclic loads during galloping, which leads to profound functional adaptation in this region. In some horses, an imbalance between accumulation of fatigue damage and repair through remodeling leads to subchondral bone fatigue injury in the parasagittal grooves, increasing the risk of stress fracture. Subchondral bone injury can be seen as focal osteolysis with standing computed tomography imaging. Articular stress fracture occurs because of intolerable subchondral bone injury. So we hypothesized that intolerable subchondral bone injury results in higher stress and strain in the parasagittal groove. We wanted to find the relationship between the adaptive response in the distal end of the cannon bone and subchondral stress and strain. To achieve that objective, we needed to build patient-specific standing CT-based finite element models of horses with and without subchondral bone injury. Hydroxyapatite electron density phantoms were scanned to calculate bone mineral density from the CT number. We segmented the distal end of the cannon bone and built a finite element model with heterogeneous elastic modulus, constrained the proximal end, and applied the 25 kN to the palmar surface of one of the condyles. We analyzed 2 specimens with no subchondral bone injury and 2 specimens with subchondral focal osteolysis lesions. Our results show that stress and strain concentration occurs in the parasagittal grooves. However, in comparison, only one of the specimens with focal osteolysis showed elevated strain levels in the parasagittal groove. On the other hand, one of the specimens with no visible injury showed elevated strain as well. This made us look into the adaptation of the condyles in these specimens. Interestingly, the 2 specimens that showed lower strain and stress, despite one of them having focal osteolysis, had multimodal distribution of voxel density in the condyles, indicative of Muir sclerosis. The other 2 specimens with higher stress and strain showed an almost normal distribution of the voxel density in the condyles. In summary, we found that increased strain in the distal end of the cannon bone is a multifactorial phenomenon caused by presence of subchondral bone injury as well as insufficient functional adaptation of subchondral bone. Also, adaptation of the condyles protects the subchondral bone by reducing strain even in presence of visible focal osteolysis lesions. Insufficient functional adaptation can expose the subchondral bone to large strains even in absence of focal osteolysis lesions. And lastly, the interplay between subchondral bone injury and subchondral adaptation should be considered to prevent false negative and false positive assessments of fracture risk clinically in cursorial athletes. I acknowledge my mentors at UW-Madison, Professor Peter Muir and Professor Corinne Henak, the students who helped with the project, our collaborator Professor Whitton in Australia, and lastly, Grayson Jockey Club Equine Research Foundation for funding this work. Thank you for listening.